Hello, everyone. Thank you for joining us. This is industry session number 2, information discovery and management. So a few housekeeping items before we start. The session is 90 minutes long. Each talk will be 15 minutes plus 3 minutes of Q&A. Now, like other sessions, if you have any questions during the talk, please type them in the chat box. We will collect those questions and ask the speaker at the end. With that, let's get started. Our first speaker is Wolfram Wingerath from Bagend in Germany. He will tell us about SpeedKit, a Polyglot and GDPR-compliant approach for caching personalized content.
Hi everybody, and thanks for joining our talk on SpeedKit, a polyglot and GDPR-compliant approach for caching personalized content. I'm Wolle from the German company Bagend, and today I'll be talking about our software as a service that we build for accelerating e-commerce and other websites. So let's get started. Hello. Yeah, presentation is loading. Just a second. Should be ready like now. There you go. Okay, that was a pretty lame joke, I admit it, but it serves a purpose, namely illustrating that nobody really likes waiting. And everybody surfs around 3.5 hours every day and waits 20 minutes of those 3.5 hours just for stuff to happen. That's annoying and costs as much as 1 year over the course of your entire life. And that's not only annoying, it's also a real business problem. So Amazon famously said that 100 milliseconds of lost page load time cost them about 1% of conversion rate. So at their size, that's about $1 billion every year. Conversely, Zalando, the German Amazon for shoes, found that accelerating their website by 100 milliseconds brought about 0.7% of revenue per session, and Walmart similarly found that 100 milliseconds of faster page loads bring them 1% in overall revenue. And the reason why page speed plays such an important role for revenue is that it also is an important driver of user satisfaction. So studies found that everything regarding the user interface delay up until 100 milliseconds is perceived as instant, and everything up until 300 milliseconds is still very good. Everything until 1 second is quite okay, but if you go beyond that, people just start thinking about something else. You know, there's a mental context switch, and eventually people just drop out of what they're currently doing. So if you have an online business, your goal should be stay under 1000 milliseconds to keep the user's attention. And it also means that page speed is money if your business is in the internet. This problem is more relevant today than ever before because due to the global pandemic, currently life is basically taking place online and overall traffic increases significantly, and at the same time we're experiencing severe drops in web speed all over the world. But even though COVID-19 may make the situation worse, the basic problems are the same as always. So first, we have backend processing for assembling data and rendering in HTML in the server, and then transferring that to the client. That may take a while if the server and the client are far apart. And even if the data arrives fast, the client still has to render everything, which may also take its sweet time. We at Bagend have made it our mission to resolve these bottlenecks. We're a research-based spin-off from the University of Hamburg that is centered around caching uncacheable data. And we carry our research into practice through SpeedKit, a software as a service for accelerating e-commerce websites. So let's talk about how SpeedKit works in detail. When a website loads, normally the browser just requests something from the origin server and then waits for the response. With SpeedKit, this is accelerated by a caching infrastructure that not only exploits CDNs, but also the local caches in the browser, so in the user device. And it's different from CDN caching because we also have a smart client proxying within the browser, so a service worker process that can decide whether it's actually necessary to ask the origin or whether the same data can be delivered faster from our caching infrastructure. In doing so, we of course exclude resources that we cannot possibly cache, for example, tracking or ad services, and we always make sure that the data in our caches is synchronized with the original content. And this is basically the main challenge here, and you could break it down to two problems. So first, we have to detect content updates, and then we have to propagate these content changes to the clients. And that's what we'll be talking about on the next slides. So the first challenge is detecting content changes, and we do that via revalidation jobs. And a revalidation job specifies what kind of content should be checked for changes. So for example, you could say, take all the HTML files, and then you can trigger that either manually or via cron jobs. And what this revalidation job here does is it queries all the HTML files that are currently cached and compares them with the cached version. So you hold the original version from the website against the one we have cached, and only those that have actually changed are invalidated in the CDN. And we also transport that information, and that's the next challenge on the next slide, to the client, so that expiration-based caches, such as the browser cache, are also avoided whenever a resource has changed. To illustrate the second challenge, let's look at a simple example. You have a user visiting a product page, and then the HTML is loaded and delivered through a hierarchy of caches. So now the user sees the HTML and its local browser cache and the invalidation-based cache, so the CDN, have the HTML with a fixed time to live, say a day or so. But now an hour later, so still within the TTL, a different user buys the product and thereby invalidates the HTML. So now all the data that the other user saw before has become stale. But we can by revalidation detect this update, but we can only invalidate the CDN, and the expiration-based browser cache would still return the stale resource here. To tell the user, so the SpeedKit client proxy basically, that the expiration-based cache has to be avoided, we apply a trick. And the trick is that we store the updated HTML file in a server data structure called the cache sketch. So that's on the bottom right. And then we transport that every 30 seconds by default to all clients, so that before loading a page, the SpeedKit client proxy can make a lookup whether the resource that is to be taken out of the browser cache is actually fresh or not. And if this test determines that the resource should or could be stale, then it's just avoided, and the browser cache is not used, but instead the CDN is used. And this gives us delta atomicity because we know that we never deliver data that is older than 30 seconds. So this shows how we make sure that we never deliver stale content from our caches. But accelerating websites is still challenging because the HTML file, which is pivotal for performance because every other resource is linked in there, is very difficult to accelerate since it's personalized typically. So what we do is we configure SpeedKit in such a way that it knows which portions of the website are personalized. For example, the hello customer badge or the number of items in your shopping cart. And then SpeedKit delivers an anonymous version of the website immediately from the caches, so very fast, and in the background loads the personalized version of the website, so for the logged in user, so that we can patch in the personalized portions later. So if you hold that side by side, you see that the anonymous version and the personalized version of the same website typically look very similar. So there's really not much disruption in your user experience if you just say, see the anonymous version first and the personalized version later, but it's really relevant for acceleration. So in a nutshell, we load the anonymous and fast version of a website from the very fast SpeedKit caches and just fetch the personalized information from the original system and patch it in later. GDPR-wise, this is an awesome concept because we do not process any kind of sensitive user information. The patching together is done within the browser, so on the user device, and all that is confidential or private in any way is stored on the original shop system, and still we can accelerate content delivery. And the key enabling technology here is service workers. So with a normal website, the browser tab just fires up a request against the network and then waits for the response. And with SpeedKit, we have the smart client proxy sitting in the middle. So that's a service worker process that intercepts all HTTP requests that are going out and then can decide whether it is actually served, so that whether the response is actually served by the requested origin, or, for example, by the cache. And that, as I just explained, serves as a mechanism for acceleration, but also can be used to implement offline capability. So it essentially turns your off-the-shelf website into a progressive web app. And one thing that is particularly beneficial here is that SpeedKit can reroute requests to different origins. So usually, for example, if you include third-party libraries in your website, like the Google Analytics or the Facebook SDKs, then these resources are served over cold and slow connections, and that really slows down your website as well. But with SpeedKit, you can just serve these resources over the SpeedKit CDN. You can't do that with any other CDN because they do not hook into the request routing into inside the browser. And another thing that just comes by default here is that we can apply on-the-fly optimizations to resources such as images. So for example, we optimize JPEGs to WebP whenever the browser supports that, and thereby just reduce the payload of served images without compromising the quality. And this is very reliable because more than 90% of all users use browsers that support service workers. And even if you have an old browser that does not support service workers, then the website is served as usual. So you don't really have degrading effects there. It's just better when you have a service worker browser and it's just the vanilla website experience else. To really get the best possible performance for our customers, we integrated a real user monitoring into SpeedKit so that we can track and monitor performance metrics like the time to first byte or various browser timings, but also user engagement metrics and business KPIs. So if we have an online shop, for example, we configure SpeedKit to know what exactly a conversion is, and then we can tell you whether your user or session conversion rate is going up or not. And we can also monitor all kinds of mistakes and errors that happen, so we can actually improve the quality of the website because we have built-in QA as well there. And what we do here is essentially we do split testing for web performance. And this is a very neat feature because no other CDN solution can actually do that because CDNs are always only on or off. So you can only compare performance in a before-after fashion. But with SpeedKit, you can enable SpeedKit, since it's JavaScript based, for only a portion of all users. And then you can say, okay, let's compare SpeedKit users and normal users at the same time on the website and collect tracking data for both of these user groups and then compute the uplift performance-wise, but also in session length and other user engagement metrics, business success, and ultimately the money that you are making by using SpeedKit. To illustrate the gains of our approach, let's look at a few customer examples. On the left, you always see the vanilla website experience, and on the right, you see the SpeedKit enhanced version. And as you can see here, for Bauer.de, which is a large German e-commerce retailer, it's a pretty clear win for SpeedKit there. If you look at the numbers, it's also clear that SpeedKit provides a significant uplift, moving the median time until the first contentful paint from above 2 seconds to 1.3 seconds. As another example, here's the German version of Decathlon, which is the world's largest sports online retailer, and we also provide a significant performance uplift there. Here we visualize the first paint performance in a different way, namely the way that Google uses in the Chrome User Experience report. And you also see that the fast experience, so below 1 second, is significantly more often achieved with SpeedKit than with the vanilla website. Yeah, and lastly, here is another customer of ours, Stylefile. And as you can see, if you hold SpeedKit and the normal version of the website side by side, it's also clear which is faster. And here we compared the business performance of SpeedKit users against the normal users without SpeedKit, and we achieved a significant uplift in both the user-based conversion rate and the average order value. Okay, it's time to sum everything up. SpeedKit offloads servers because it serves resources from the CDN that would normally be requested from the origin server. Thereby, it reduces latency and improves the overall customer experience. And that concludes our talk. Thanks very much for your attention. As a closing thought, we are publishing ongoing results on the impact of web performance on business success at speedstudy.info. So if you're interested in what we do, check that out. Yeah, otherwise drop me a line at voller@bagend.com or ask questions now. Thank you.
All right. Thank you, Wolfgang, for the very nice talk. I don't see any questions from the chat yet. If there's any questions from the audience, feel free to unmute yourself and ask now. Okay, so I have a very short question. So you mentioned that there's a schedule of some sort that's used to determine if content is stale or not, right? So it sounds like there's a possibility of false positives. What's the typical accuracy that you observe?
No, that's there's a chance of a actually false positive in the sense that we store in this cache sketch data structure all the resources that have changed while their TTL is still valid. So if you have something like, okay, we cache it for 1 day and then it changes after 5 hours, then we put it in that data structure. But it's a Bloom filter based data structure. So okay. You basically, if you cram many resources in there and you then do a lookup, the client might say, okay, possibly this HTML is in that cache sketch. So possibly it is stale. So I better take the CDN. And the worst case scenario is basically that you take stuff from the CDN, even though you could have used the local cache, but you are guaranteed to get the fresh result. So I think it's something like if we have 20,000 resources and we store like 5 kilobytes for that cache sketch, it's like 5% false positives, but that's like really an extreme scenario. And I mean, that's just performance. It's never correctness.
Okay.
Thanks
good.
for the question.
All right. So if there's no more questions, let's move to the next presentation. Our second speaker is Qingchen Gu from Georgia Tech. His talk is titled D-Health, All Your Online Health Information Belong to Us.
Hello, everyone. My name is Qingchen Gu. Today, I'm going to present our paper, D-Health, All Your Online Health Information Belong to Us. Nowadays, the healthcare services has been rapidly transforming from the traditional hospital clinics model into the digital world. Patients can easily search for information related to their diseases or symptoms, asking for questions related to health problems from the health professionals, or even fellow patients who share similar symptoms. The online health services has been growing rapidly in the US. Around 59% of US adults have employed the internet as a diagnostic tool in 2012. On average, the US consumers spend around 52 hours annually to search for online health information, while they only visit doctors 3 times per year in 2013. It has also been shown that at least 60% of the US internet users perform online medical searches before visiting their doctors to better understand their symptoms, or after seeing the doctors to better understand their treatment. In fact, there is a large amount of user health data available online. The largest health-related forum in the US is called WebMD. It has around 183 million monthly unique visitors and 14.25 billion page views. Another major health-related forum is called the Health Board. It has around 10 million monthly visitors, 850,000 registered members, and 4.5 million health-related messages. An internet user can easily browse through these forums to search for health-related posts. More importantly, one does not even need to register for an account or only need to spend a few minutes to register for an account before viewing this information. This means that the private health information of the users are publicly available. As a result, there have been many events related to health information leakage. For example, in 2019, it has been found that unauthorized access to computer servers have impacted 2.9 million patients, which began as early as 2010. Another incident, also in 2019, is related to 1.5 million patients' health data being breached. And there are many more other similar events, which is a great threat to users' online health data information. The problem with protecting online health privacy lies in the fact that existing techniques focus on protecting the privacy of data from hospitals, clinics, labs, and other traditional places. These data are structurized medical health data. However, these techniques can hardly be applied to online health data because the online health data are usually heterogeneous and structurally complex. The scale of the records of users in the online health data is also in the order of millions, compared to the order of tens of thousands in the traditional health data. And finally, compared to online health data, the dissemination of structured traditional health data is easier to control. Therefore, a privacy compromise is less likely. Due to its open to public nature, however, the dissemination of online health data is difficult to control, and adversaries may employ multiple kinds of means and auxiliary information to compromise data's privacy. In our work, we study the privacy of online health data using two online health forums, WebMD and Health Board. We propose a de-anonymization framework called D-Health and present a linkage attack framework which links 12.4% target WebMD users to real-world people. We find most of their full names, medical information, birth dates, addresses, and other sensitive information. Therefore, those users' privacy can be compromised, and one can learn various aspects of information such as sexual orientation and related infectious diseases, mental, psychological problems, and even suicidal tendency from some users' medical data. In our work, as mentioned earlier, we collect data from WebMD and health boards. In WebMD, we collected around 540,000 web pages, and in health boards, we collect around 2.5 million web pages. We then extract features from these datasets. There are three types of features that we use: the user correlation graph, Stylometric features, and user data attribute graph. In the user correlation graph, patients are connected by symptom, disease, and discussions. One user can start a thread under a defined topic related to a disease and start posting about their symptoms or diseases, followed by other users joining the discussion and posting their own symptoms and diseases. Therefore, we can construct a user correlation graph based on relationships among the posts of different users. Each user is represented as a node, and two users posting under the same health disease topic share an undirected edge. We also assign a weight to the edge based on number of shared topics between the nodes. The second type of features is called stylometric features. Stylometry is the use of writing style for author attribution. It has been widely applied in many areas outside of author attribution, including fraud and deception detection, underground cybercriminal analysis, or even programmer de-anonymization based on their programming style. The major advantages of stylometric features include the difficulty for users to intentionally obfuscate their writing style or attempt to imitate others in a long term. Therefore, this feature is very stable for a single user. This table lists the categories of stylometric features we use, which includes the length of letters in a word, the length of a word in a sentence, the richness of vocabulary, and the letter frequency, digit frequency, uppercase letter percentage, and so many other features. The third type of features we use is called the user data attribute graph. It is based on the stylometric features of each user and extended from the correlation graph. In the UDA graph, each node still represents a user. The attribute set of each user is determined based on the stylometric features. Each post of a user can be analyzed with stylometry and generate a list of attributes which correspond to the post. And all the posts of a user can be combined to generate a list of attributes that is owned by this user. We only considered each attribute as a binary feature, which means either it exists or does not exist for the user and do not account for the weight. Therefore, each pair of nodes share a weighted edge based on the number of shared attributes in their attribute sets. The UDA graph takes into account both the data's correlation and the linguistic features. Using these features, I will explain our de-anonymization framework called D-Health. We use two data sets called the anonymized data delta 1 and auxiliary data delta 2. We extract features as mentioned before and transform the data sets into graphs G1 and G2. For every anonymized user in G1, we seek an auxiliary or non-user in G2. Here, a natural question arises. Are delta 1 and delta 2 generated by the same group of users? The answer is not necessarily. Therefore, we divide the problem into two scenarios. The first scenario, called closed word DA or de-anonymization, defines the scenario where all users in delta 1 belongs to the users in delta 2. The second type of scenario, called open word DA, describes a scenario where part of the users in delta 1, but not all, belong to the users in delta 2. And in this work, we apply our methods in both scenarios. The D-Health framework is consisted of two phases. In phase 1, we perform a top K DA, which means we generate a list of top K candidate users that could be a match for the target user. In phase 2, we perform a refined UA based on the top K candidate users and select the most likely user that can be corresponded to the target user. In the first phase, top K DA, we compute the structural similarity between each anonymized user and each auxiliary user. The structural similarity is based on the degree similarity, distance similarity, and attribute similarity. The details of this similarity can be found in the paper. After obtaining the structural similarity scores, we compute the top K candidate set for each user. We propose two approaches for the selection: the direct selection and graph matching-based selection. In direct selection, we directly select K auxiliary users that have the top K similarity scores with the target user. In graph matching-based selection, we first construct a weighted completely connected bipartite graph, where the weight on each edge is the structural similarity score between the two corresponding users. We then find a maximum weighted bipartite graph matching. For each pair of users in the matching, we add the auxiliary user to the top K candidate set of the target user and remove the edge between the target user and that auxiliary user in the bipartite graph. We then repeat this process until we find a top K candidate set for each target user. In the second phase, called refined DA, we train a classifier using the Stylometric and correlation features and conclude whether the target user corresponds to some auxiliary user or it does not correspond to any user. We employ benchmark machine learning techniques such as the support vector machine, nearest neighbor, or regularized least square classification. The good news is existing benchmark machine learning techniques are satisfiable at addressing the closed word DA problem. However, the bad news is the performance is far from expected in the open word DA. To address this issue, we present two schemes, false addition and mean verification, which are motivated by the open word author attribution techniques. In a false addition scheme, when de-anonymizing a target user, we randomly select K-prime users from the auxiliary users that are not included in the candidate user set, and add these K-prime users to the candidate set as false users. Then, if the target user is de-anonymized to a false user in a candidate set, we conclude that this user does not exist in the auxiliary user. This means there's not a match for the target user in the auxiliary dataset. Otherwise, the target user is de-anonymized to a non-false user. We present our experiment results using these figures. The figures on the left shows the cumulative distribution function of the correct top K de-anonymization in the closed word. The correct de-anonymization of the top K means the matching auxiliary user is included in the top K candidate set. We vary the value of K and show the performance of the top K de-anonymization with different amount of training data set. On the right-hand side, we show the accuracy of our de-anonymization method with the highest accuracy of over 70%. We show similar results for the open word scenario. As we expected, the performance of the de-anonymization is slightly lower in the open word scenario. We can see that based on our analysis and experimental results, online health data privacy suffers from serious threats. Unfortunately, there is no effective solution for protecting the privacy of online health service users from either the technical perspective or the policy perspective. Therefore, our results in this paper are expected to shed light in two areas. Number one, for our de-health and linkage attack frameworks and evaluation results, they're expected to show users, data owners, researchers, and policymakers the concrete attacks and the corresponding serious privacy leakage. And number two, for our theoretical analysis, it is expected to provide researchers and policymakers a clear understanding of the impacts that different features have on the data anonymity and can help facilitate them to develop effective online health data anonymization techniques and proper privacy policies. Thank you for listening to my presentation, and I would like to welcome any questions you may have. Thank you.
Okay, thank you, Qingchen, for the nice presentation. Any questions from the audience? Okay, I have a quick question, Qingchen. So you mentioned that you can link about 12% of your target WebMD users to their real-world identities. So this is very interesting. What are the real-world identities that you are linking to? Are those like Facebook accounts or voter registration records?
Yes. First, can you hear me?
Yeah, I can.
Okay, so we search on real name-based social network services like Facebook or Twitter, mainly Twitter, and we were able to find those users using the name search and avatar search, which is like Google image search using their avatar image, and also we were able to know that like so sometimes you may have different users that share the same username, which is pretty common. Like you could be called David, the other people could be called David in their username as well. But so we use like an entropy measure So with a higher entropy means it's more likely that the username is unique, and that means you are you. If you are named something like CJack1358, then it's most likely nobody else will have the exact same username. So we rank the users by their entropy first, and then search for names to find a match on the social network services.
I see. So basically, you construct the ground truth manually by yourself.
So it's like a semi-automatic process. We do a search first, and then we do manual verification.
I see. Okay, cool. Okay, so looks like there's no more question from the audience. Let's move to the next presentation then. Our next speaker is Zhenyu Hu from Huazhong University of Science and Technology. He will tell us about Maxson, reduce duplicate parsing overhead on raw data.
Hello everyone, my name is Hu Zhenyu from Huazhong University of Science and Technology. Today, I will introduce you Maxson, a cache system to reduce duplicate parsing overheads on raw data. In many web and enterprise applications, JSON is a highly popular data exchange format. The features of JSON include flexibility, simplicity, immutability, and so on. And many data analytics engines like Spark, Flink natively support loading and querying JSON data. A JSON text is a sequence of 0 or more JSON objects. It begins with a left brace and ends with a right brace, and contains a sequence of 0 or more key value pairs separated by commas. Let's take an example to show how JSON data is stored and queried in data warehouse. Table T has 3 columns: MoID, date, and cell logs. Cell logs stores the sales information in JSON string format. The following 2 queries retrieve the item with the highest turnover and the highest cell count in a 3-day window. In these 2 queries, the function getJSONObject is used to retrieve the specified field. This function requires 2 parameters. The first one is the column name to specify the JSON string. The second one is JSONPath. It indicates the path to the specified field. For example, the JSONPath $turnover indicates the path to the field turnover in cell logs. Unlike relational data, JSON is a semi-structured format, and that has to be passed before further analysis and query. Unfortunately, parsing JSON data is expensive. In order to demonstrate the overhead of parsing JSON data, we test 3 types of queries, which appear very frequently in the production workload. Query 1 is a simple select query. It retrieves 2 attributes from the queried JSON data. Query 2 uses count aggregate function with a group by condition in JSON fields. Query 3 performs a self-equal join. It's very obvious that parsing JSON data accounts for the majority of the execution time, more than 80%. Even both simple data retrieval and more expensive queries with join and aggregations. In recent years, many researchers are devoted to reducing the cost of JSON parsing. Next, we will introduce 2 typical solutions. The first one, published on 17th VLDB conference, it presents a new JSON parser that uses SIMD instructions to build a field index for a JSON string. The field index is based on special characters such as brackets and colons. It can perform efficient projection without deserializing JSON string completely. And the second one, published on 18th VLDB conference, it adopted a new approach that applies filters on long byte string of data to reduce unnecessary JSON parsing. It's based on the observation that many real-world applications are high selectivity. While these approaches can effectively reduce the overhead of JSON parsing in a single query, but in production workloads, many queries may have correlations. Is there any room for further reduction for the queries with correlations? We start a study with a real production workload from Alibaba. We collected a 5-month query trace from a deployed data analysis system and found that these queries exhibit significant temporal and spatial correlations. Among these queries, about 82% queries are recurring, and the JSON path involved in these queries follows the power law distribution. About 89% of traffic is on 27% JSON path. On average, each JSON path will be requested by 14 queries. We further study the time of table updates during the day. Updates are more frequent at noon, but real at midnight. Furthermore, the data that has been appended will hardly be changed. Only 2% of the tables experienced modification of appended data. Based on the above observations, we propose to develop a cache system named Maxson for catching the values elevated from JSON path for reuse. We look for simple and effective caching strategies for the production workload. Also, we hope that our system can cause minimal changes to existing data analytics platforms. Maxson is designed to be fully compatible with SpecSQL. First, we develop an effective machine learning-based JSONPath predictor to determine the JSON path which should be cached. Training data comes from the historical data table. A scoring function would be used to choose the JSON path that can provide the highest benefit. JSON path catcher is used to retrieve the value. Second, to enable queries can make use of the cached JSON path. A query plan modifier, Maxson-Parser, is implemented. Because of the cache, a part of the data of each record comes from the raw data table, and another part of data comes from the cache table. These two parts of data belonging to the same row need to be stitched together correctly to form a complete record. Here is the overview of JSONPath Predictor with combining long short-term memory and conditional random field model. It predicts whether a given JSON path will be accessed at least twice on the next day or not. In other words, it predicts if a JSON path is a multiple passed JSON path on the next day. The input features include JSON path, date, and count, which is the access time of the JSON path on the specified date. And the output is the multiple passed JSON path, which will be accessed on the next day. When a user submits a job to SpecSQL to take advantage of the cached tables, we modify the physical plan for table loading phase. We use an example to illustrate how it works. As the above the figure shows, it's a simple query that retrieves the values of more ID, date, and passes the item name and item ID in the cell logs. Then, filter the item ID which values greater than 10,000. We assume that both item ID and item name have been cached. The Spark physics plan needs to project the 3 columns. They are more ID, date, and cell logs, and it needs to pass cell logs to get JSON object function to get item ID and item name. While in the Maxson physics plan, cell logs is removed, replaced by 2 placeholders. The values of item ID and item name are read from the cache table instead of bypassing cell logs. Finally, we will execute the modified physics plan. We start two readers to read their values. The one just reads the uncached values, called primary reader, while the other one that reads the cached values is called cache reader. JSONPath cacher guarantees the cache table input split and the raw data table input split are aligned. They have same number of rows. We pass the color names by the configuration of the readers, and we group value together according to the field index contains in the physics plan. Since we cache JSONPath values separately, if the predict contains a cached JSONPath, we can use it to restrict the rows that should be read from the raw data table and the cache table. For the above example, row group 0 contains ID less than 10,000 is completely skipped. We implement Maxson over Spark version 2.3.0. The experiments run on a 22-node cluster, and for the predictor, we use the LR, SVM, MLP classifier, and LSTM as our baselines. And for the Maxson, we use the Jackson, Mason as our baselines. We use F1 score to elevate the effectiveness of the predictor. From the left table, we can find that temporal features are very important in our scenario. And from the right table, we found that when the time window is 1 week, we get the best F1 score. In this experiment, we use 4 different cache constraints to examine our scoring function. We examine 2 strategies to get multiple parser JSONPaths. The one is the scoring function, and the other one is randomly snagged. Also, we show the query performance without caching. As the above figure shows, the scoring strategies always outperforms random caching with different cache limits. The average cache overhead for each query only accounts for 1.7% of the execution time. That's because many queries with spatial relationship can shred the cache overhead. In summary, the speed ups achieved by Maxson are ranging from 1.5 to 6.5 times. To make a closer comparison, when we break down the running time of 2 queries into 3 steps, read, pass, and compute, the results are shown in the above figure. In Maxson, we admit the overhead of passing by reading the cached value from the cached table. Besides, Maxson's input size is much smaller than Spark's input size. Because the filtering predicts include properties within the JSON string, so we can push such predicts down into the cache table to reduce the number of records that are read. This experiment is to answer the question of whether it still makes sense to cache JSONPaths given that there are efficient JSON parsers. Maxson still has the overhead of projecting data fields, which is especially significant when the JSON schema varies greatly within the dataset. Therefore, we can see that for query 2, query 3, query 4, query 6, query 7, query 9, and query 10, the caching in Maxson is more effective in eliminating the parsing overhead. Besides, Maxson can be a good complementing technology for Maxson to speed up the parsing of the uncached JSON paths. Finally, let us summarize today's talk. We identify temporal and spatial correlations among different queries in terms of JSON path access. We develop effective machine learning-based predictor which determines the JSON path to catch given the space bandwidth. We propose Maxson, a JSON path cache system that's implemented as a component in spec cycle to reduce duplicate parsing of JSON, and the source code of Maxson is available at GitHub. That's all. Thanks.
Great. Thank you, Zhenyu, for the very interesting talk. I don't see any questions yet. Okay, so a very quick question. So you showed a nice comparison with random caching. Do you have a sense of how these would compare to other classical caching policies like LRU, for example?
Hello, can you hear me?
Yeah. Mm-hmm.
Yeah. In the experiment, we make a comparison with LRU cache policy,
Okay.
and the result shows the LRU effective. How to express it? Let me think. Oh, okay. The LRU cache hit ratio is less than the less than our cache strategy, because we can predict the JSON path that will be accessed from the user's access history, but the LRU is based on the user's current history, so we can make a high hit ratio.
Okay, cool. Okay, so any more questions from the audience? Okay, if not, let's move to the next presentation. Our next speaker is Lishen Zhao from East China Normal University. He will tell us about automatic calibration of road intersection topology using trajectories.
Hello everyone, I'm Lishen Zhao, a student from East China Normal University, School of Data Science and Engineering. The topic of my paper is automatic calibration of road intersection topology using trajectories. Our objective is to find the missing or incorrect turning path within road intersection, and based on then calibrating the road map. The outlines of my talk as follows. The first part, I will introduce the motivation of our work. The second part, challenges. The third part, stress solution overview, and then experiments and applications. Finally, a conclusion is given. PD Chuxing handles more than 40 billion routine requests every day. The accuracy of intersection topology is very important step will have an impact on those aspects. First one, the driver safety, as is reported by TTG Media. 4 British tourists were killed in a collision because the driver made a long U-turn at an intersection. And the second is the user experience. Data leads to poor user experience. And third, platforms' economic benefits. Inaccurate navigation will cause user complaints and user churn. How incorrect connections at intersection are displayed in trajectory data. Let's see the examples. Both in blue denotes the trajectory hit. Line in right denotes load map. The left picture in red circle is load segment missing, and the middle picture shows U-turn missing. Since they are not added into the map, the driver detoured. And the right picture, the passing trajectory deviating from the load map. This will affect the accuracy of navigation. In order to calibrate them, we first need to locate the intersection. Let's see the right picture. Existing technical emphasize on identifying the core zone. It includes the location and coverage of load intersection. Our solution can identify not only the core zone, but also the influence zone, including spatial connectivity and routable topology. And as far as we know, there is no work attempts to calibrate the intersection topology before us. However, we face some challenges, such as low quality data due to signal interruptions and signal drafts caused by internal equipment issue or external human factors. The sampled position points may be uncertain and even abnormal. And uneven data distribution. It's hard to infer the topology of region with sparse trajectories. Load intersections are of various sizes and shapes. Similar turning behavior with no intersection. Load connectivity may change over time because of traffic flow and load infrastructure maintenance. All this brings interference to load intersection topology calibration. In order to solve these problems, we put forward the following framework. We call it as CITT. It's composed of trajectory quality improving, core zone detection, and topology calibration. Next, for a detailed interpretation. Consider the low quality trajectories may result in errors. We employ the strategy consists of segmentation, denoising, and simplification to improve the quality of low trajectories. There may be a large time interval or distance gap between two consecutive trajectory points because of GPS signal interruption. And segmentation generates a few trajectories of short length or few points, which cannot completely show the load geometry. Such trajectories are viewed as noise data. We eliminated them with outlines. And we used the Douglas-Poker algorithm to simplify each trajectory into a set of key points to reduce computing costs. As is shown in right, the trajectories become smoother and have few noise through quality improving procedure. And to solve load intersection of different sizes, we split the observing region by employing a top-down division method. Next, we selected the candidate region with intersections using direction-based clustering. Then, we used the mean shift algorithm to detect the center position of intersection. Next, according to the density of the turning points gradually decrease in the annulus outwards, we got the coverage of load intersection. After location and identification, we got the trajectory in intersection influence zone. Next, we made similarity measurement between the trajectories and use the dbScan clustering algorithm to distinguish between different turnings. To get a smooth turning path, we adopted a 3-step trajectory consisting of force attraction adapting, phase-based sampling, and B-spline smoothing. Force attraction-based method makes the trajectory inside the class more compact. And for phase distance sampling, we randomly selected 5 trajectories as candidates from each turning cluster. We calculated the sum of the phase distance between one candidate and other candidates. We choose the smallest one as centerline. And to restore the shape of the turning path in a more realistic way, we use the B-spline method to smooth the centerline. Next step, map matching. To figure out the missing turning path or turning path with position offset, the extracted turning center lines match with the existing roadmap, finding and match the center lines. We utilize hidden Markov-based map matching method. Meanwhile, we adopted convex QO-based sub-roadmap strategy to speed up matching process. And we conduct experiments and applications to prove the effectiveness of CITT. We used 4 data sets. They are shuttle bus trajectory data from University of Illinois at Chicago, car trajectory data in Futian district of Shenzhen from Didi Chuxing, and open stretch map road map data, Didi road map data set. And we also used the 4 comparison method. The first one grouped the high density cells where turns fall into clusters to find the intersections. And second, treated the endpoints of unmatched parts as the vertices of the constructed roadmap through map matching. And the third, try to obtain cluster centers using k-means clustering and regards those centers as the vertices in the road network. And the fourth, generated the road center line of missing roads using sweeping line method. Among them, we evaluated the former 3 methods for verifying the effectiveness of our intersection location detection strategy. And we chose HYMU method for proving the accuracy and stability of our center line fitting strategy. We implemented a facial comparison evaluation on both data sets. The intersections are depicted in yellow spots in CITT method and the red spots in CBTB. The results in picture shows that CITT method can detect more intersections and be more accurate on both data sets. Next, we measured the matching degree of each detected intersection with its ground truth by 3 averaging criteria, including precision, recall, and F1 measure. CITT always performs best according to 3 averaging criteria because CITT can find the intersections with different sizes effectively. Next, we implemented a facial comparison averaging on Centerline fitting between CITT and HYMU. Picture results show that CITT is more accurate and more robust than HYMU. Besides, we did a calibration experiment on the DD trajectory data. In the experiment, we have 101 abnormal test cases. 69 were detected correctly. There are 58 turning path deviation, 11 turning path missing. Some cases were not detected because of no trajectory. And conclusion. We present an effective framework called CITT, including quality improving, core zone detection, and topology calibration within influence zone to offer a solution based on high trajectories to the inaccuracy issue of load intersection topology. We designed a Centerline fitting mechanism, including force traction, adapting, pressure-based sampling, and B-spline smoothing to ensure the accuracy of extracted turning path. We have calibrated more than 3,000 incorrect connections in the DD roadmap so far, and the entire process is highly automated. In our future work, we will implement link-level topology calibration at load intersections for precise navigation purpose. Okay, that's all. Thank you. If you have any question or advice, welcome to contact me.
Okay, great. Nice talk. Thank you, Ethan. Any questions? Okay, I will start with one. So you mentioned that on one of your test sets, there are 101 test cases and your method can detect 69 of them correctly. So on the remaining cases, do you have a sense of why those are not detected? Hello, Lishan. Are you still here?
Hear me? Can you
Okay,
hear it?
I can now.
Because there are no trajectories passing these test cases. Because in the original digital map, people didn't know the road in the navigation, and so there are no passing trajectories, so we cannot detect it. Yeah.
Okay, cool, great. Yeah, looks like there's no question from the audience. Yeah, I guess people can also follow up with you offline if they have any additional questions afterwards. So for now, let's move to the last talk of this session. And our speaker is Qitao Shi from Ant Financial Services Group. He will tell us about SAFE, Scalable Automatic Feature Engineering for Industrial Tasks.
Hello everyone, I'm Qitao Shi, an engineer from Ant Financial Service Group. Now I will introduce a recent work, SAFE, Scalable Automatic Feature Engineering Framework for Industrial Tasks. Machine learning techniques have been widely used in almost all internet companies and serving as essential parts in diversified fields, such as advertising, recommendation, risk control, and smart medical. With the help of these techniques, excellent performance and significant improvement have been obtained. To build a machine learning system, a professional machine learning pipeline is always needed, which usually includes data preparation, feature engineering, model generation, and model evaluation. And the performance highly depends on the quality of the features. Thus, generating a good feature set becomes an important step to achieve high performance. However, since human experience are greatly required, feature engineering becomes tedious and time-consuming. And with the growing need for machine learning techniques in industry tasks, it is impractical to perform feature engineering in all of these tasks. This promotes the birth of automatic feature engineering, which is an important topic of automatic machine learning. The goal of automatic feature engineering is to generate new features based on the original features by using some operators, so that machine learning models can achieve better results on the new features. Several studies have been conducted on this topic. Some methods are based on reinforcement learning. These methods require many rounds of attempts, and it is necessary to generate a new feature set and evaluate it in each round, making them infeasible in industry tasks. Some methods are based on transfer learning or meta-learning. However, a large number of experiments on various datasets are needed to train these methods. And it is hard to introduce new operators or increase the number of parent features. Some methods follow the generation selection procedure. However, these methods always perform as generating all legal features in the feature generation stage, and then selecting a subset of features from them. Thus, the time and the space complexity is extremely high. In industrial tasks, the size of real business state is always very huge, which introduces extremely high requirements for space and time complexity. At the same time, due to the rapid change of business, there are also high requirements for the flexibility and the scalability of the algorithms. Besides, there are more requirements that needed to be addressed, such as hyperparameter insensitive, distributed computing, and real-time inference. We approach the problem from the typical two-stage methods and propose a method named SAFE. As shown in the figure, SAFE is an iterative process where each iteration comprises of two phases: feature generation and feature selection. The number of iterations is limited by the calculation time or computation space. In the feature generation stage, different from the previous methods, which focuses on what operator to use or how to generate all legal features, we focus on meeting the original feature pairs that generate more effective new features with higher probability to improve the efficiency of the process. In the feature selection stage, we propose a pipeline with the consideration of the power of a single feature, the redundancy of feature pairs, and the feature importance evaluated by tree model. It is suitable for multiple different business states and various machine learning algorithms. The search space is so large that we have to narrow it down. We first train a tree model, ChargeBoost. Our algorithm is based on two basic assumptions. For unary operators, features that are generated based on split features are more efficient than that generated based on non-split features. For other operators, new features that are generated based on split features, which from the same path, are more efficient than from different paths, where the latter is still more efficient than features that are generated based on non-split features. We verify these two assumptions in experiment. Based on these two basic assumptions, we can find the features or feature combinations on these passes for feature generation, which not only greatly reduces the search space, guarantees efficiency, but also ensures the validity of feature generation. To further narrow down the search space of feature generation, we use the information gain ratio to sort the features and the feature combinations in the search space. The split features and split values can divide all records into several parts. Then, information gain ratio can be calculated. Features or feature combinations with the highest information gain ratio will be used to generate new features by these operators. Users can choose or expand according to their business needs. The operators act on original features for feature generation, and it can be divided into unary operators, binary operators, and so on. Unary operators are used for discretizing, normalizing, or mathematical transforming. Binary operators combine two original features to generate a new feature, such as four basic operators, logical operators, and circle-based operators. It should be pointed out that there are still many operators that apply in specific fields. We call them domain-specific field operators, such as lag operators in time series analysis, genetic operators in biology, and so on. Candidate features that are composed of the base features and the generated features might not be of equal importance. To select the more informative features, we use a three-step process. Firstly, according to the information value, the features with low predictive power are removed. Then, the redundant features are removed according to the Pearson correlation coefficient. Finally, the remaining features are sorted by using ChargeBoost. Consider general industry data. The time complexity of our algorithm is shown on the slide. We can easily control the number of features generated and the time complexity of the algorithm by controlling the total number of trees of ChargeBoost. The time complexity and the space complexity of our algorithm is very low and can be adjusted flexible according to actual needs. Therefore, the number of samples, the type and number of features and operators can all be flexible changed. The hyperparameters which needed to be set in advance are only used to control the complexity of the algorithm. Every aspect of our algorithm can be easily parallelized, and users can choose different operators to meet the real-time requirements. We compare our model with the original features. Two other state-of-the-art feature generating algorithms, FC-tree and TFC, and two of our own comparison algorithms, safe-random and safe-important. Safe-random algorithm randomly selects different feature combinations of all original features for feature generation. Different from it, safe-important algorithm only randomly selects different feature combinations with the split features of ChargeBoost for feature generation. Safe-random and safe-important follow the same feature selection process as safe. They also choose the same number of feature combinations. We evaluate the generated features and also the original features of each compared algorithm on 9 classification algorithms. We conduct experiments on some benchmark datasets with different sample and feature size. The reported performance are measured by AUC. It can be seen SAFE has a significant advantage over all other compared algorithms, no matter what model is performed after the feature generation process. Compared with the original feature space, the features generated by our model can improve the overall prediction AOC by 6.5% on average. Compared with FC3 and TFC, SAFE can improve the performance by 2% and 3.7% on average. What's more, SAFE performance better than SAFE random and SAFE important, indicating that our algorithm does mine a combination of features that are more likely to generate better features. We combine the original features with the top-ranked generated features to form a new dataset and use random forest to score feature importance. It is evident that the new features generated by SAFE are more important than the original features, which validates the effectiveness of the generated features. We have analyzed the time complexity of each method. Here lists the actual executing time. It can be seen that SAFE has a great advantage. This proves the efficiency of our algorithm. Experiments on large-scale business data sets are further conducted. As we can see, the number of samples is extremely large, up to 8 million training samples for day 3, which hinders the employment of many other methods. Thanks to the delicate design of SAFE, the whole time consuming is acceptable even for the industrial tasks. More important, SAFE can improve the performance. Actually, this framework has been deployed in our system, providing help for many different real-world tasks. Automatic feature engineering has become an important topic of AutoML in recent years, and many different methods have been proposed to handle this task. However, the efficiency and scalability of these methods are still far from satisfactory, especially for industrial tasks, where automatically performing feature engineering is demanded. Here, we propose a scalable and efficient method named SAFE for automatic feature engineering. Extensive experiments on both benchmark datasets and extra large-scale business datasets are conducted, and the detailed analysis is provided, which shows that the proposed method can provide prominent efficiency and competitive effectiveness when comparing with other methods. That's all. Thank you.
Okay, great. Thank you, Chitao, for the nice talk. Any questions? Okay, so I have a question on how this is being used in production at your company. So are these being used with humans in the loop, or is this fully automated? Because even though feature engineering is very important, for end-to-end AutoML, there are also things like model selection and hyperparameter tuning. So is your framework used in conjunction with those additional components, or is your component being invoked by developers as a standalone tool so that the features that you generate can be leveraged by those engineers?
Okay, 这个auto machine learning can be split by auto feature engineering and model selection and hyperparameter tuning. And our work is not means that we don't need to do model selection or hyperparameter tuning, and model selection and hyperparameter tuning can based on our new features.
I see.
Yeah.
Okay, so in production, looks like you have additional components that are doing model selection, hyperparameter tuning, which are built on top of your component. Is that right?
In this paper, I haven't done the model selection and hyperparameter tuning.
I see.
Yeah.
Okay. Okay. But how is this used in production?
based on our methods, we will generate some new features, and then we can use some models that based on some auto machine learning algorithms or some or based on some people's experience.
I see. Okay, cool. So if there's no more questions, yeah, I think we will close the session now. I would like to thank all the speakers again for the excellent presentations. And thank you everyone for calling in. This is the last session of today. So we will see you back tomorrow at the conference. Okay, bye.